feedback here. Hello. Okay, is it better? Yeah, I think it's better now. Excellent. Okay, let me share my screen, and I probably need someone to tell me if they can see my screen now. Can you see my slide?
Yes.
All right. Thank you, and welcome to everyone on the International Day of Light celebration. My name is Sudarshan. I work at IIT Madras. I just joined 3 months ago, and today's talk will be on integrated photonics. Before I start, I'd really like to thank Suresh, Binu, and Kailashnath for inviting me and setting up this talk. So I just wanted to start with 2 slides because I was not sure the exact audience that I was going to be talking to, but something that actually happened after I joined here, which was, I would say, particularly not very inspiring, where when I had a discussion with someone and explaining what I work on and explaining what photonics was and using the word optics now and then, the final impression I seem to have made with the person was that I essentially train students to prescribe glasses. So I just wanted to perhaps set a common footing, at least to those who perhaps have the question in their mind as to what exactly is photonics. And why did we need this rebranding? So we had the perfectly good term optics, and suddenly for some reason in the last 40 years or so, this term photonics came into being and has sort of swept the entire world. So this photonics sort of started around the time when the semiconductor lasers were invented and demonstrated, and I think was really enhanced in popularity and usage after the fiber optic communication revolution. So why the word photonics? Essentially, the idea was that for optics was going to slowly replace functions that were traditionally done using electrons or electronics, right? So I think they wanted a term that sort of sounded like electronics, but to claim that it's the functionality that was being carried out earlier with electrons is now going to be done using photons, right? So that was the main purpose of this rebranding. And I think photonics now, I think, is the more common term that people tend to use for a wide variety of applications. And why exactly is photonics so important, and why is integrated photonics relevant in today's world, right? So I see a lot of students in the audience in the glimpse that I got in the video. So at least to the students, humans have certain basic needs, right? And I'm going to try to put this in the context of why this technology is going to be useful. And as our communities have grown in sophistication and our communities have become more complex, the governing bodies have obviously expanded this list of human needs to a larger and larger word cloud that now includes things like education, healthcare, sanitation, transport. And more recently, I would say in the last 30 or 40 years, data has become extremely important, right? More so that we're trying to bridge the digital divide gap within the country, and trying to make sure that the internet is accessory to everyone, right? Regardless of their economic background. So why is photonics important? here's why I think it's important, right? And the group here believes photonics is important, right? And there are many backers for this, right? We fundamentally believe that we are going to improve the basic human condition in many, many ways, right? And photonics, and specifically integrated photonics, is going to impact every single word that you see in that word cloud, right? So it's fundamentally going to change the way the food is going to land on your plate. It's going to change the way manufacturing is done. It's going to change the way people look at power, right? Energy needs, and the way we do basic work in terms of transport and education. So if you don't believe me, obviously I have a small snippet of our recent Nobel laureate who worked on what she calls photonic hammers. I hope a lot of you have heard her and heard her talks and read her research on chirp pulse amplification. So in 2018, Donna Strickland won the Nobel Prize for creating short pulses of high energy photon pulses. And it was her belief, and she said this about 3 or 4 years ago, that photonics is really going to be the technology of the 21st century. So if we thought digital electronics was the technology of the 20th century, 21st century is going to be changed, or its photonics is going to leave its imprint on this century. So that's why I think as students, you are in the perfect position to equip yourself for the jobs of tomorrow by staying in photonics. So with that sort of footing, I kind of want to transition. So photonics is a very, very large area, and I can only give you a glimpse or sort of the tip of the iceberg by giving you some examples of work that I have done in this field, right? And much of the projects that I worked on were mostly funded by the Department of Energy. And why was the Department of Energy concerned with photonics at all? And I'm going to develop that motivation and try to tell you why or how my research falls into improving our energy situation as we see it today, right? So the energy equation is fairly simple, right? So there's energy input, and that can come from renewable or non-renewable resources. As most of you know, that we mostly rely on non-renewable resources today, and there is a big push to move towards solar and wind and other renewable resources of energy. And then there's some work that we'd like to do, right, through some process, and that process has a certain efficiency. And the outcome is essentially some work, useful work, and waste, right? So the equation is fairly simple. Most of you know this from a very young age, right? But here are some facts that I have on the slide. Today, the reality is we waste more energy than we consume. So the arrow that marks waste is significantly bigger than the actual work output that we do, right? And which is why it's very important as students that you pick up work or projects or ideas that help us in reducing or recycling wasted energy, right? So you can think of taking this wasted energy and then feeding it back in sort of a feedback cycle, right? So there's some research work going on that as well, but fundamentally improving the process efficiency is also very, very important, right? So when it comes to really performing functions, right? I see two main functions that we try to mimic. One is the skeletal and muscular function. So we created the transport and manufacturing sector that's trying to replace manual labor. But if we look at it from a purely energy efficiency point of view, right? Some of our gasoline cars today, and even some of the hybrid vehicles and even the battery operated ones are barely struggling to get to the efficiency of us as humans, right? And when I say 25% efficiency for a human, it's sort of a crude calculation from the energy that we get from the calories that we eat from our meals and food to the skeletal energy or muscular work that we can actually perform. Say, for example, walking a certain And certainly this efficiency can be improved with mechanical advantage. So if you were riding a bike, obviously that's going to give you a lot more distance that you can cover with minimal effort, right? So I've not brought that into picture. But interestingly, it doesn't really mean that we cannot work on this anymore, right? That, oh, we have similar robotic or machine functions that can provide as much efficiency as humans can do. But unfortunately, the human efficiency has come down in the recent years, right? It's mainly because the energy it takes to bring the food onto your plate is actually very inefficient. So you would probably hear people saying that it's better to eat local, right? Eat the food that's locally grown, so you don't have to transport your food from very long distances in inefficient trucks, and then having to use refrigeration to keep them unspoiled by the time it reaches your plate. So there's still a lot of work, and I believe photonics has a large part to play in that as well. And there's a field called agri-photonics that's slowly becoming very, very popular. But I think the one that I was more drawn to is the brain function, right? So the aptitude work that we do, the cognitive sense. So here is just an example of what happened several years ago. I think you all probably heard that there was a supercomputer, AlphaGo, that beat Lisa Doll in a game. But the thing that sort of went under the carpet was that the AlphaGo machine was actually consuming 85 kilowatts, which is about 1,000 times more than what Lisa Doll was operating on with his brain, right? So this is significantly different. So we're not talking about 2 or 3% order efficiency. We're talking about 3 orders of magnitude in terms of energy efficiency, right? So we really need to consider this problem, challenging problem of how can we actually make mimicking brain function, right? Which is a lot of the artificial intelligence and machine learning related work that we're doing increasingly today. How can that be made more efficient, right? So that's the key question that we all wanted to answer in the program that I was funded over the last 10 years. So as a subset of that, we looked at data crunching, right? And I think this is a slide that's probably been splattered over in several talks. I probably don't want to bore you. The amount of data that we're creating today, it's exponential. And I think the one thing that I probably want you to get out of this slide is really understanding exponential scaling. I think one thing that sort of slips people's mind, whether it's people at all levels, right? Whether it's people doing research or whether it's people funding the research. One thing that slips people's notice is the scale at which things grow, right? And linear scaling as opposed to exponential scaling are 2 very different forms of scaling, right? And I think trying to grasp that itself requires some careful calculations. So what do we do with all this data, right? A newfound craze for most companies is, can we actually make sense out of this data? And a lot of this data has a very short lifetime, right? So for example, if you were to try and book a holiday today, you go into some website, tries to give you a complete package of the hotels that you can stay, the car that you can rent, and things you can do in and around the city. So they try to make a vacation package for you, and that is very short-lived, right? The prices of the hotel rooms, from the time you search, things keep changing and evolving as others book into the room and things like that. So we generate a lot of data, but a lot of this data actually is very short-lived, right? So people want to be able to crunch large volumes of data, but in a very short amount of time to make sense of them. Otherwise, the value of the data actually goes down, right? But then there's also some back-end processing that we can do with data. For example, medical data that actually has a lot more retention time. But the common factor in all these data processing aspects is we have machines, so-called data centers or high performance compute clusters, that's chugging through all this data, right? In a very brute force method. And we've built so many data centers now that we have a projection that these data centers put together might actually have a carbon footprint that's more than some countries put together, right? And this is already data that's old, right? This is using data from 2007 and 2015. So there's probably more updated numbers, but this is where the scare comes from exponential growth, right? So as opposed to something that grows linearly over time versus something that grows exponentially over time, even small error bars can give you very large mismatches in projected demand versus the actual reality. And what exactly is happening in these data centers in terms of energy, right? Surprisingly, more than half the energy that the data center consumes just goes into cooling the machines. It's not actually going into doing the number crunching. That's fascinating to me when I heard this the first time, right? And Google seemed to have a lot of hiring that they do in people who are experts in like mechanical cooling or like cooling techniques, right? Being more efficient in cooling and things like that. They're not even hiring people in people who can do machine learning or although that's an important sector, they have a large workforce that's just dedicated into how can we make this cooling system efficient. So the vapor, the gases that you see coming out of these towers is water vapor. So there's not much of a concern in terms of a greenhouse effect. But I think the fundamental concern from these cooling towers is just how are we going to reduce the amount of cooling requirement on the machines over time, right? If we're going to keep scaling the data centers. So if you look at what exactly we're cooling, there's essentially three components, right? So these server racks, they have storage, there's compute, and there's networking, right? So much of my PhD days spent on how can we make networking more efficient. And more recently, through my jobs, I've also looked into how can we make compute more efficient, right? And remember that the efficiency improvements that you make at this level, wherein how much energy per calculation that you want to make, or how much energy you require to move certain data from one point to another point, actually scales beyond one-to-one. So if I scale a watt in transferring 100 gigabits from point A to point B, I'm not just saving 1 watt. I'm actually saving 1 watt, but I'm also saving power that I need to cool that because my processors or servers run cooler. So I don't need as much cooling power as I did before, right? So, which is why efficiencies at the lowest level can actually scale to larger efficiencies when you look at the data center as a whole, right? Which is why a lot of money was invested through several projects across the country to look into bringing efficiency gains at the fundamental network level, right? So I'm going to be looking at optical networking or optical communication and how can we improve the efficiency in those links, right? I hope I'm making sense and you're able to follow me, right? So if anyone has doubts, I'm open to questions. Perhaps we'll take it at the end, just to not break the flow of the talk. So if you have some questions, please note them down and we can take them one after another in the end. So what is happening in the data centers in terms of networking, right? One thing was a lot of the short distance communications are still being done in copper, right? So you wouldn't be surprised if you walked into a data center. I think India itself has several data centers. So if you students get a chance to make a road trip to one of these data centers, I would urge you to go take a look behind these server racks and take a look at how data is actually moved from point A to point B. And a lot of the connections are still in copper, right? And the reason is simply a factor of both cost and as well as optics not being as efficient, I would say. So if you look at chip to chip or edge to edge, the data movement energy, so you can see that it's a tapered graph. So if you can see my mouse pointer here, the red dots show the photonic links and the blue dots are the electronic links, right? So at very close short distance communications, there's really not much of a gap, right, that you're creating between an electronic link versus a photonic link. But the places where the contrast is more dramatic is when you look at rack to rack or system to system or across the data center. Right? So you're looking at orders of magnitude improvement in energy efficiency by going to photonic links. And another interesting feature, which I think if you've gone through any fiber optic communication course, the instructor would keep telling you this fact, is that optics destroys distance. Because the loss per unit length in fiber is just independent of frequency and it's so small compared to electronics or running electrons in a cable because of skin effect, that you basically don't see an efficiency change by scaling distance, right? Whether it's a back-to-back communication or a long-haul communication, as long as there's no repeaters, the optics pretty much stays put in terms of energy efficiency. Whereas electronics, it scales with distance. The longer the cable that you need to connect two places, the more is the loss, right? And the loss is even more severe when I'm trying to go to higher and higher frequencies, or I'm trying to communicate at a much larger data rate. So the idea here is really to push the boundary in distance from traditionally long haul versus local area network based communications where photonics is dominant. We want to push that boundary so that we actually consider optical communications for board-to-board connections or rack-to-rack connections as well. We're not quite there for chip-to-chip, but remember that for this cursor to move from where it was to where we want it to be, from an energy perspective, also means that we have to bring down the cost. So if you want to convince current day data center operators to make a switch, they need to be able to convince not just from performance perspective, but also from a cost perspective. If you told them that switch to optics and you'll get 10x bandwidth, but you have to pay 10 times more or 100 times more, they might actually think twice, right? So the economy of scale and bringing down the cost per link is very, very key. And like I said, the energy efficiency doesn't change much from distance because the optical fiber loss doesn't change much, which means that much of the inefficiencies in optics comes from where you encode the data from electronics to photonics and where you decode them back from optics to electronics again. So let's look at those ends first. So to see why, how we can make photonics at scale and also bring down their cost, right? So we looked at electronics and we see that over their 5 decades of work, they've gone from a single transistor on a wafer to several billions of them on wafer, right? So that law of scaling has essentially not just given us improved performance, but has also improved or diminished the cost per transistor, which is why we are able to enjoy the luxury of a cell phone per person on the planet, right? The question is, can we see a similar scaling in photonics? And we hadn't looked into large scale miniaturization or scaling out photonic circuits for a long time. And the fundamental reason for that is because in electronics, once you look at materials, silicon is an extremely good waveguide material, which is it's transparent to the wavelengths that we use in fiber optic communications today. But fundamentally, if a material is transparent to some wavelength, means that it will also will absorb less, right? Or it will be a poor emitter of light. So if we need both emitters and absorbers of light and a material to guide light at the same time, it's going to be a difficult challenge. It cannot be the same material fundamentally, right? So we need some way to be able to integrate materials that generate and absorb light together with materials that can actually safely carry that information across without losing much of it with low loss, right? So that's where the group that I had joined, it's Professor John Bauer's group in UC Santa Barbara. And they, in collaboration with Intel, had come up with this technique of trying to mate 3-5 materials to silicon wafers, right? And this was the first time anyone had demonstrated this. And the reason it's a challenge is because 3-5 materials in silicon don't share the same crystal structure. And they also don't expand equally with temperature. So they have a mismatch in the coefficient of expansion, which makes these two materials not want to bond to each other, right? So the process of bonding was new, that had to be invented, that happened, and it basically gave birth to what we call the heterogeneous silicon platform. So we want to use silicon wafers because it gives us the advantage of having to use machinery that we conventionally use to make your CMOS ICs or VLSI ICs. But we also want to be able to do photonics with it, not just transistors. But here is an idea which says that let's use traditional circuitry to do everything that we want to do on silicon first. And in a backend process, let's attach materials that we need to generate and absorb light so that we now have a compact form factor for an entire transceiver to be built on a single substrate. And the reason why this is important that we do this in silicon is explained in this figure here. So you can see how using a 300 millimeter silicon wafer, which is quite typical. In fact, much of the CMOS industry has gone to even bigger wafers now. You can see how many dyes we can get in one shot, right? As opposed to what is traditionally done in an indium phosphide wafer, which is about 6 times smaller in diameter, which means it's 36 times smaller in area, right? So you're getting a factor of 36 from just going from a smaller indium phosphide native substrate wafer to something that's much larger. It's not just a question of size though. There's another big advantage, and that is the accuracy, right? So some of these tools that process at 300 millimeter size silicon wafers can actually improve in optics and the resolution of the features that you get on the wafer, right? So one of the key challenges is how uniform are the features end to end in a given wafer, right? It's not very useful if you did your process in a big wafer, but only the central dyes are yielding, whereas the outer dyes are not yielding because of improper feature size or a feature mismatch between the center dyes and the peripheral dyes. That's not very useful, right? So it's very important to also realize that there's so much engineering that's gone into making these 300 millimeter silicon wafers so uniform that an edge die is just as good as this die at the center, right? So imagine how much of work has gone into the lithography systems and the lens systems to get the precise aberration-free critical dimensions in the sub 200 or 100 nanometers across the entire wafer. I think that's engineering marvel in itself. And I think photonics really wants to ride that wave. And as the CEO of Intel at one time, Ratner, said, the photonics industry has no clue what's coming to it, because they have been able to integrate indium phosphide and 3.5 based lasers and detectors onto such a large silicon wafer platform that you can now conceive of doing all the tests and qualification and everything that follows wafer manufacturing completely in an automated sense, right? So that's completely changing the economics of scale of the cost of what it takes to make a transceiver today, right? And remember that this challenge was not being done by just one group. right? And it's been approached by several research groups and several companies. And here's just a snapshot of a few of how people think that this will evolve over time. And the one that I showed in the previous slide, which was where I worked, was molecular bonding, but people have tried polymer bonding, which in some sense is sort of like using a glue attach. There's also microtransfer printing, where you actually do the entire processing of the 3-5 dies. And then you just pick and place those in places that you want them on the silicon wafer. And there's also places where they have tried bonding prefabricated lasers. You still produce lasers in these tiny 50 millimeter indium phosphide wafers, but then you pick and place each one of these wafers that are tested and known to be good, and then you tightly package them with the silicon photonic die in order to be able to couple light in and out, right? And people have done this either using end-fire coupling, which is just another word for edge coupling, where light transmits from one edge to the other. And there's another which is called coupling with gratings, where light couples out of this normal of the wafer, right? It's a surface normal coupling where the light leaves the wafer in a perpendicular direction to the wafer flat. So there's many techniques that are still out, and there's not a clear winner, right? Although I can safely say that Intel's gone the way of molecular bonding, and they're already shipping millions of units of optical transceivers, and they're seeing a lot of success in the market, which is very promising as photonics engineers. And really, here is a slide from IBM, who looked into the packaging side of things and really saw that the reason for why they think silicon photonics is going to be a major player in the future is because we are fundamentally changing how the cost structure of how what is involved in making a transmitter, right? And a transmitter, I'm going back to what I said, where much of the cost in the optical links comes at the end points, where you're transferring electrical energy from electrons to optical energy in photons and the optical fiber, because fiber is dirt cheap, right? Fiber is just glass. So focusing on the endpoints and the transceivers and trying to change the way we manufacture these is going to change how we look at photonics and how pervasive it's going to be in our lives in the future, right? And here is a very nice slide. I've stolen this from the first student of my advisor, actually, Radha, who clearly tried to demonstrate the power of size reduction from integration. So the boxes on the top and the bottom are what it would take from a conventional gold box packaged lasers and detectors and multiplexers and SOAs. And if I were to make a 100 gigabit transceiver with a transmitter and a receiver, you can see how many components is being packaged into something that's just a few millimeters in size. So this is a tremendous reduction in size. And remember that a lot of this, once it's integrated, doesn't require the hermetic sealing anymore, right? So once you've packaged and things are covered in oxide, you don't have the usual concerns of catastrophic optical damage at the edges. So you don't have to hermetically seal them, worry about moisture getting into these packages. So all in all, I think integration just fundamentally removes a lot of constraints that were originally there in terms of packaging optical components, right? So you can think of these chips just as another chip that you see in your cell phone. So you don't see your cell phone packaged in a hermetic seal, right? Or in a gold box, right? It's just open. If you just open your back case, which is getting harder and harder these days, but if you do manage to pry open the back side, you just see the PCB and all the chips facing and exposed to the outer environment. So we didn't stop there, right? So as a community, the integrated photonics groups all across the world, after this idea of trying to integrate dissimilar materials onto silicon, didn't stop with just 3 5s. they went on to show that other materials can also be integrated, right? And the reason is photonic is really inundated with a lot of exotic materials specific for a function that you would like to implement. For example, nonlinear optics requires fairly different materials. For an isolator, you need a garnet material, something that has non-reciprocity. And then you have lithium niobate, which is a fairly linear, has very good Pockels effect, because some of these semiconductors lack these because of symmetry in their crystal structure. So I think the theme for integration still lingers on. So it's not just about integrating gallium arsenide and indium phosphide on silicon anymore. The question is, can we integrate the relevant materials that we need in a fashion that's actually conducive to large scale manufacturing, right? I think that has become a fundamental question that people want to answer today. So what I want you to take out of this talk ultimately is picture anything that's optic or photonic today, whether it's in research labs or it's in companies. And the idea of integrated photonics is, can we make this smaller? Can we make it power efficient? And can we reduce its cost, right? And you will find that integration answers a lot of these questions, right? So with this in mind, I'm sort of doing a time check. So I'm at the 45-minute mark. So I'll give a quick overview on the projects that I have begun looking into and would like to pursue as research going forward. So if any students are interested, this is sort of like an advertisement for what's happening in IIT Madras as an integrated photonics group here. So if any of you feel that these topics are interesting, please spread the word that IIT Madras is involved in these areas, and that way we can grow as a community to share and make sure that photonics reaches everyone, right? So the first concept is FPGA, which stands for Field Programmable Photonic Gate Array. And this, I think, was spearheaded by Jose Capmany in Spain, where they came up with an idea that the barrier to entry for making a photonic chip is quite high, because you rely on fabs and using these multi-project wafer runs. The cost does come down, but it's still quite a bit of a barrier of entry for many research groups, right, to pay for those kind of multi-project wafer runs. So what they thought was, could we make something that's more general purpose, like in electronics, like an FPGA, where you could build in many optical functions with a single optical lattice, right? So that we print these, and many in number, regardless of what project you are doing or what functionality you'd like to get from photonics. Could we use the same building block or the photonic array and then add the peripherals depending on the project that you would like to work on? That could substantially bring down the cost, right? And I think it's a fantastic idea, and it's picked up very quickly. And a lot of companies are also trying to get onto this bandwagon and actually implement it in some way. And I really hope that this scales and actually provides people all across the world with affordable chips that they can actually use for complex functionality. And obviously, this is not a trivial task, because there is the electronics that drives the photonic arrays and the software that helps in configuration of these programmable arrays. So there's still a lot of work that needs to be done before these can be distributed at a global scale. But this is a very interesting point of research. And in IIT Madras, we have someone who is championing this effort. His name is Bijoy Das. I'm sure most of you have heard him, have met him perhaps. So here's just an advertisement for the CPPICS work that we do. I'm part of this group now. And our vision is to essentially build something of an ecosystem that's indigenous and can actually help anyone who'd like to make sure that their ideas in integrated circuits or silicon circuits a reality, in terms of something physical that they can hold and show people, right? And not just a research paper or a concept diagram or an IP or a patent, right? So we want to go beyond things on paper to actually things that are printed on silicon and doing actual demonstrations with them, right? So that's the overarching goal for the CBPICS program, and we hope that it'll continue to grow in the years to come. And then a little bit of an aside, this is sort of my pet area of interest. My dad worked in ISRO, so I naturally had an inclination to space technology right from when I was young. So I also see that there is a significant impact that integrated photonics can have in space technology, where currently things are done using conventional optics like concave mirrors and lenses, and they can actually be removed. And a big advantage of that is you reduce the payload, right? And remember that every space launch, the cost of something you want to send to space is proportional to its weight, right? So the lighter your gadgets are, the lighter your experiment is, the more chances they are of succeeding or getting a chance to get to space. So the idea here is to actually use an imaging sensor that uses silicon and silicon nitride at the same time, because silicon can absorb visible wavelengths very well, and silicon nitride is transparent there. So by combining these two materials, I think one can actually make some pretty cool sensors and imagers. And finally, I think I'm involved in another project that's spearheaded by Anil Prabhakar. I think a lot of you know him. He is our local guru for quantum mechanics and quantum optics. And he works in QKD, both in quantum computing and communications. And we are right now trying to develop a chip that essentially brings the entire set of components that's marked in this red dotted box, right? So that's the delay line interferometer, the phase modulator, the drivers, the FPGA board that generates the timing, and then the TDC chip, the intensity modulators. Except for the source and the single photon detector, we'd like to get everything onto a chip. And here's just a cartoon schematic of how we think it'll look like at the end of the project. And we have, this would probably be the first demonstration in the country of its kind that is trying to integrate several functions into a heterogeneous package, what we call a multi-chip module, that's extremely miniaturized. And in theory, at least this is my strong belief, that its QBER, or the quality of the link that you can create, should be better, right? And it should also be faster. So let's hope we reach that end goal. So just as a final word of advice, I'd like to just let people know, especially students, that products are no longer single entities, right? And the greatest example is your cell phone, right? There's gallium arsenide chips, silicon chips, all for specific functions like amplification, computation, and photonics is slowly going to creep into all of these gadgets. So you're going to find yourself saying that a common PCB in an electronic or a digital device that you hold has electronic chips and photonic chips, right? So equipping yourself with photonic engineering is a key skill to have in the future. And second, a product building will require people from different area of expertise. So it's going to need people from a particular area not to silo themselves in their research work, but to actually proactively interact with other groups, right? So the photonics group needs to know the concerns of electronics, and the electronics group needs to know the fundamental limits of photonics, and vice versa, right? So the cross breeding or interaction across teams is going to be an essential feature and has been something that I've seen in my experience in the companies that I've worked in. So please make sure that you try to keep yourself interdisciplinary, make sure that you equip yourself with necessary knowledge to interface between other products and other technologies, and make sure that you voice the importance of photonics in areas that you see fundamentally in your heart that there is an advantage in using photonics for that purpose, right? So with that, I'd like to again thank you all for the time and would like to wish you a happy International Day of Light 2022. So yeah, any questions? Actually, I see it being muted. Okay, you're back. Does anyone have any questions?
One question.
Yes, sir.
So this is just, so do you have any collaboration with Samir, IIT Mumbai? Or
no, sir. I joined in January, so it's only been 3 months. I'm slowly only introducing myself to a lot of people. So I definitely want to reach out to as many people as I can, and would like to collaborate as much. So I think part of the reason why I accepted this talk was also to really find out who else is interested in this area and for potential collaboration in the future. So I'll certainly take down this contact of yours and try and contact him soon.
So one more point.
Yes, sir.
I am an ex-faculty of CUSAT.
Okay.
I'm an ex-faculty of CUSAT, and I have learned that there is a lot of work going on in the area of integrated optics. That is why I asked.
Okay.
Okay.
Sure. Yeah. I would be more than thrilled to have collaborations across institutes, because it's mostly just Bijoy and myself championing the integrated aspect of things over here. Anil sort of providing fuel to the flame now and then, but we definitely want to make a bigger case for integrated photonics in India. So the more the merrier.
Okay, thank you for your excellent talk.
Thank you, sir.
So good morning. On behalf of ISB and Samuel, to propose a vote of thanks, let me thank our chief guest, Assistant Professor Sudarshan Srinivasan, for spending his valuable time and giving us an excellent presentation of integrated photonics. Thank you, sir.
Thank you all.
Next, I would like to invite Dr. Suresh Nair, Chair, IEEE India Council, Chair, IEEE Photonic Society, to share a few words on the special occasion. Welcome, sir.
Thank you. Good morning. Good morning. Good morning. So, first of all, I would like to thank Dr. Sudarshan for giving such a wonderful talk. And my international day of greetings to all of you. Last year, the theme for International Day of Life was mainly, I think it was trust science. That was for 2021. This year for 2022, it is mainly basic sciences for sustainability and glass. That was written. Why I have mentioned this one, it's like when you are photonics students in faculty, there are three basic aspects in science, technology, and industry. First one is the basic research, which is being done in various national laboratories like Academic Research and things like that, where we come up with a basic fundamental scientific principles. My point is like the output from that, the basic science should get on to the next phase. That is basically applied research. That's what you can see. Professor was also talking about that one. Like from the basic principles, they are trying to come up with the device or the product. Being an IIT, you may be some sort of a proof of concept and sort of low volume production and all. The output from these type of laboratories normally is like publishing patent and things like that. It was like that, but now I think mainly to come up with the products which can be used in the systems. So whatever expertise from these labs, the applied research labs, should now get on to industry. So these are the three things.
Applied research and industry. So these have to work together. Then only, the industry will be able to come up with the products. It can be commercial products which will help the society and things like that. That's how the whole cycle completes. So those who are interested, you will have some aptitude towards theory or applied research or industry. Please, look for opportunities. Lot of opportunities are there. For example, IIT Madras, Dr. Bijay Das has talked to you some time back. I think 2 or maybe 2 months back or so. Anil Prabhakar also, Dr. Anil Prabhakar also, we have tried to invite him, but he was busy this time. So you have enough opportunities even to do research, PhD at IIT Madras. In this group, you can see a lot of students from ISP also doing these type of research activities, and ISP has got a good name also. So with that, I think I should thank each one of you for participating, and that's all. Bye from me. Thank you. Vinu, you want to say? The organizers are here.
Good morning. International Day of Light greetings to all. So as part of this celebration, we are conducting some other events also. One is a photography contest. So the theme of the contest is Light in Science, Art and Everyday Life. The deadline for submitting the photos is 15th June. And then another event is an innovation challenge. So in that, you have to present an innovative idea that use optics and photonics. So that can make an innovative product, a technology, an application. So you have to present it in a 10 minutes time. So there is a registration link is given in the poster. So that registration, you have a deadline that is 15th June. So the selected members, means participants, will have to present this idea on 18th June at International School of Photonics. So please participate in all these events and support us.
So thank you everyone for joining us for this celebration. Hope we will have a much more detailed celebrations in the next year onwards. This was the first year after the IEEE Photonic Society was established in this department. And thank you one and all once again.